Okay, so section 6.3 is something called the multiplication principle. And we had looked at, before all this stuff with the coronavirus, we had three flavors of ice cream: vanilla, chocolate, strawberry. And suppose we had two types of cones, sugared cones and unsugared cones. And again, the problem is we want to count how many ways can this occur. I have to be careful about different because when we get the combinations, we're going to be dropping that in some sense. And so what one could do is draw out a tree diagram where you have vanilla and sugared cone, unsugared cone, etc. So you have 1, 2, 3, 4, 5, 6. So we could count it by brute force like that, which is going to be horribly inefficient. So we try to come up with a better way of doing this. And the idea is really very simple. It's called the multiplication principle. When you have independent objects that you're picking, you just multiply the number of choices that you have. So we had three flavors and two types of cone. 3 times 2 is 6. And suppose we add on additional toppings, excuse me, like sprinkles, nuts, gooey stuff, whatever. So then we could take the sugar cone and do these types of toppings and these types. That's ridiculous. You're not going to do this in general to try to list out all the different possibilities. So we use the multiplication principle, which says I have 3 types of flavors, 2 types of cones, 3 types of topics. Just multiply them. 6 times 3 is 18, and we're done. Let's go back to our horse racing problem. We have 5 horses: Alice, Bob, Cindy, Dave, Ed. Okay? And you're making a bet based on first place, second place, third place for your horses. So in other words, you have to bet and guess in the correct order who the first place finisher is going to be, who the second place, and who the third place. Suppose you bet on A, B, and C, but actually what comes in is A, C, and B. You do not win the bet because ACB is not the same as APC. Another positive thing is notice that you can't have horse C come in both first place and last place, third place. That doesn't make any sense. So once a horse is used up, that's it. You can't. It can only take one place. Now, we don't want to get into discussions of like ties and things like that. We're just trying to illustrate. So the question is, how many different ways would you have, because we're going to be talking about probabilities, to actually do the correct bet? Well, you would have to go through things like this: A, B, C. So I'm going to take all the possibilities where A comes in first. So it could be BC, or it could be CB, or A, B, and D, or A, B, and B. That's going to be a huge number of things to do. The multiplication principle will save us very quickly. If when I'm running this race, well, when the race gets off, there's 5 horses. Any one of those 5 could come in first place. Now we have no idea which horses are better, which are not, blah, blah. So now once I pick one of those horses, I'm not telling you which one it is. We now have, 4 horses left. So then I pick one out of there, I'm not telling you which one it is, and that means you now only have 3 horses left. So that means you had 5 that can come in first, 4 that come in second, 3 that come in third. You multiply it. 20 times 3 is 60. So that means if you have no idea which horse is going to come in, no insider information, nothing like that, you have a 1 out of 60 chance of picking the Correct course. Let's take a look at another example. A homeowners association is going to elect a chair and a secretary. There are 4 candidates for the chair, 5 candidates for the secretary. Now notice that here we have a distinction between the types of positions. A secretary position is not the same as a chair. A chair position is not the same as a secretary. So how many different ways can we do this? Well, we just multiplication principle. There's 4 candidates for the chair position, 5 for the secretary, so there's a total of 20. Simple enough. A library wants to display 2 rare books. So what we're saying is we have a library, like the Library of Congress, whatever, and we have 2 very prestigious slots where we're going to be putting 2 rare books. Now the library has 50 rare history books and 125 rare literature books. How many different ways can the books... So we could take 1 out of the 50, put it here. We could take 1 out of the 125, put it here. And then we could switch those. Well, you are not going to do this by hand. Okay, there's no way. Multiplication principle says, look, I have history books and literature books. They're completely different. Multiplication principle just says, whoops, this should have been a 5. Let's fix. So let's fix that. Excuse me, I should have put it in 125. I did multiply correctly, but I just didn't put that here. So there's no way you're going to count this up by hand. That you're not going to do this by brute force. That's insane. Let's take a look at another example. So all we're doing is using the multiplication principle. It's very easy. All you do is multiply your choices. So let's say we have a quiz that has 4 multiple choice questions with 5 possible answers. So that means we have like A, B, C, D, and E, right? And we have 4 questions. 4 questions, 5 possibilities. So the question is, how many ways could the quiz be answered? Multiplication principle. The first question has 5, right? We're just randomly choosing 1 out of 5. 5 answers, possible answers for the second question. 5. Multiplication principle. 25 times 25 is 625. The point of that is it's probably not a good idea to guess, right? Because you're not going to probably do very well. All right, now this is, we're going to have to put our thinking caps on. I have 3 couples and they're attending a movie and are selected in a row, or seated, in a row of 6 seats. How many different seating arrangements are possible if couples are seated together? Okay, so let's think about this. I have 3 couples, which means I have 6 seats. And the question is, how many ways can I do this? Now, so let's make a picture. Notice no formulas. I have seat 1, seat 2, seat 3, seat 4, seat 5, and seat 6. All right, so if I put a couple, that means I could have one person here and or I could flip them, right? So I don't start switching with couples. So for example, couple 1 doesn't get switched with somebody in couple 3. So in other words, if we write down what these are, so I'm going to say couple 1 are the A's. The little subscript means this is the first member of couple A, the second, etc. So I have 3 couples, and before you cheat and look at the answer, I want you to take a few minutes. So I'll pause this, and I want you to take a few seconds and think about what would you do? How would you attack this problem? Okay, so here's the situation. Let's do this piece by piece. I have a couple here, a couple here, and a couple here. Now, any one of the 6 people can sit in here, correct? You guys with me? Now, once I've made that choice, do I have any choices for who is going to sit in this second seat? The answer is no, because the couples have to sit together, correct? So once I've chosen one of the 6 people, we know there's only one person that can what? Sit in the second seat. How many people are left? 4. Remember, you have one person here, one person here. You've used up 2 out of the 6, which means you only have what? 4 left. What does that mean? One of those 4 people can sit in this slot, which means there can only be one choice to sit here. Okay, how many people do I have left now? Well, I've taken out 2 more, so we now have a total of 2 people. So what's happening here is multiplication principle just says 6 times 1 times 4 times 1 times 2 times 1, which turns out to be 48 different ways. So this is how we do use the multiplication principle. And we're going to obviously have more examples. See you next time.